Today, we're taking on the heart. But we're not going to treat it like just another organ. No, we're going to think of it as a perfectly engineered machine, and we're going to deconstruct it piece by piece to really see what makes this incredible engine tick.
So, what's our game plan? First, we'll dive into its amazing dual pump system. Then, we'll check out the brilliant one-way doors that keep everything flowing correctly. After that, we'll track down the electrical spark that gives it life, see how the body's control panel tells it to speed up or slow down, and finally, we'll talk about what it takes to keep this engine running smoothly.
Okay, let's get right into it. You see, the heart's biggest, most amazing trick is that it runs two completely separate delivery routes at the exact same time. It's this incredible feat of parallel engineering happening inside you this very second.
And here, you can see those two routes in action. The blue loop, that's the pulmonary circuit. It's sending blood that's out of oxygen on a quick trip to the lungs for a refill. At the same time, the red loop, the systemic circuit, is pumping all that fresh, oxygen-rich blood out to the rest of the body. Two pumps, one organ, working in perfect sync.
So let's break that down. The pulmonary circuit is kind of like a short local delivery route, a quick hop over to the lungs and back again, just to pick up oxygen. But the systemic circuit, that's the long-haul journey. That's the one delivering that precious cargo of oxygen to every single cell, from the tip of your brain to the end of your toes.
Which brings up a really interesting question, right? If you've got these two pumps working side by side, why aren't they built the same? Why is one side of this engine so much more powerful than the other?
And the answer all comes down to the job it has to do. The left ventricle, the one that powers that big, red, long-haul circuit, its wall is literally 2.5 times thicker. Why? Because it has the massive job of forcing blood out to your entire body, and it's built with the raw muscle to get it done every single time.
All right, so let's move on to the next piece of this machine, flow control. To make this whole two-pump system work, the heart has to make sure that over a lifetime, billions of gallons of blood only ever go in one direction. So how does it do it?
This solution is just brilliant. A set of 4 perfectly designed one-way doors we call valves. Think of your heart as a little 2-story house with 4 rooms. 2 atria up top, 2 ventricles down below. These valves are like the doors at the exit of each room, and they absolutely guarantee that blood can only move forward, never backward.
And check this out. This is what those doors look like from above. On the left, they're open, letting blood rush through. And on the right, they've snapped shut, forming a perfect leak-proof seal to stop any of it from flowing back. It's just this simple, elegant mechanical design that works flawlessly, beat after beat.
You know that lub-dub sound a doctor hears with a stethoscope? Well, get this. That's not the sound of the heart muscle squeezing. It's the crisp, clean sound of these valve doors slamming shut in perfect time. The lub is the first set of doors closing, and the dub is the second set shutting just a fraction of a second later. Slam. Shut.
So, what's driving all this mechanical action? What's the signal that tells the heart to beat more than 2.5 billion times in an average lifetime? You might think it's the brain pulling the strings, but it's not. The heart has its very own, incredible, built-in power source.
It's all thanks to this amazing property called automatism. It's the heart's unique ability to generate its own electrical rhythm, completely independent from the brain or anything else. And this is why, amazingly, a heart can continue to beat for a little while even after it's been removed from the body. It's truly wild. And the command center for this whole operation is a tiny little patch of cells you can see right here, the sinoatrial node, or SA node. Just think of it as the engine's main spark plug. It sits up in the right atrium, and on its own, it fires off the electrical pulse that kicks off every single heartbeat you've ever had.
We can actually map that invisible electrical journey. And when we do, it creates the famous EKG signal the doctors use. And every part of this wave tells a story. That first little bump, that's the atria contracting. The big spike in the middle, that's the powerful ventricles firing. And that last bump is everything just resetting for the next beat. It's a complete diagnostic report on the heart's electrical health.
Okay, but wait a second. If the heart is running on its own power, how does the rest of the body have any say? You know, how does it know to speed up when you're running or slow down when you're relaxing? Well, that's where an external control panel comes in.
The body uses 2 competing systems to tune the heart's speed. You can think of it like driving a car. The sympathetic system is the accelerator. It floors it during stress or exercise, telling the heart faster, stronger. The parasympathetic system is the brakes, gently telling the heart to ease up and slow down when it's time to rest.
And it's not just nerves, you know. The heart is also constantly listening to chemical messages that are just floating around in your blood.
Hormones like adrenaline act like a turbo boost, while different ions can have a calming, slowing effect. It's this complex dance of feedback and adjustment happening all the time. And because of this incredibly fine-tuned control system, your heart is an absolute workhorse. Even when you're just sitting still, it's pumping over 5 liters of blood every single minute. Now, to put that into perspective, that's basically the entire volume of blood in your body getting circulated from head to toe once every minute. So for our last section, let's talk about what this all means for our health. Because even a machine that's this close to perfect can sometimes run into trouble and need a tune-up.
One of the most dangerous problems is when that beautiful electrical system just descends into total chaos. Instead of that clean, rhythmic signal, you get this, the messy, erratic line at the bottom. That's called ventricular fibrillation. The heart muscle isn't pumping anymore, it's just quivering uselessly. And that is a life-threatening emergency.
And this is where a defibrillator is so crucial. Now, a lot of people think it jump-starts the heart, but that's not quite right. It's more like a hard reboot on a computer. It delivers one massive shock that forces every single heart cell to fire at once, wiping the slate clean. And in that silent moment right after, the hope is that the heart's natural pacemaker, that SA node, will reboot and take over again with a normal, healthy rhythm.
And this really gets to the core of why any of this matters. Understanding how this engine works isn't just a cool science lesson. It's one of the most important things we can possibly do for our own health. Because, as this says, cardiovascular issues are the #1 cause of death in the world today. This knowledge is literally vital.
So I just want to leave you with this one last thought. Your heart beats over 100,000 times a day, every day, for your entire life, without a single break. When you really stop and think about the power, the precision, and the sheer endurance of that machine inside your chest, isn't that just the most incredible thing you've ever heard of?